If you ask me which instruments I regularly use in my lab, you will hear multimeter, oscilloscope, component tester. And since quite some time, I ask myself, how is it possible to build such a versatile component tester for less than $10? After looking at the minimal parts count of such a device, I'm convinced the inventor was a genius. Let's have a closer look. Component testers, sometimes also called transistor testers, can deal with most of our parts like resistors, transistors, capacitors, and so on. In this video, we will learn how this can be done at minimal cost. Find out why I think the inventor was a genius. We also will learn about the different fingerprints of parts like NPN or PNP transistors. And maybe you also learn some tricks on how to use the pins of your Arduino or ESPs. You will see why the ESP8266 is 5 volt tolerant. Let's start with history. According to an article on Hackaday, Markus Freyek had the idea and did the first implementation of such a tester. Then Karl-Heinz Küppeler and others enhanced the design as well as the software. In the end, the Chinese started to mass produce the devices. This is why you find many different implementations. All are based on the original design and software. But as quite often, Markus and his friends do not get mentioned. This is bad behavior of the Chinese. After this video at least, you know the history. All models have a few things in common. They have 3 test pins, a display, a button to start, and a battery. In addition, some have a nice looking graphical display and some a rotary encoder driving an extended menu system. My first transistor tester had a small alphanumeric display and was only capable of dealing with transistors, diodes, resistors, and some capacitors. As you see, I added a 3D printed case and a switch because it is only used for short moments. The switch was not necessary. I learned that the 9 volt battery lasts forever, also without a switch. It has a 5-pin socket for the 3 test pins, as well as areas on the PCB to connect SMD parts to the test pins. This tester was mainly replaced by this one because I wanted to be able to measure inductors. The new one has a bigger display and a 40-pin SIF socket, usually used in EEPROM programmers. The last one I got has all that plus 3 cables to connect directly to parts. If we want to test a part, the first question arises immediately. How do we connect the legs to the test pins? And where can we input the type of the part, whether it is a resistor, a capacitor, or something else? The first question has a simple answer. Even if one tester has 5 and the others have 14 pins, all devices have 3 test pins. The remaining pins are somehow connected to these 3 pins. Usually you find the numbers on the PCB close to the pins. They are labeled 1, 2 and 3. Pay attention. Not all devices use the same principle. For example, this one has a weird assignment on one side of the socket. The next questions: which test pin is used for what? Where is ground? Where do we have to connect parts with only 2 legs? And how do we have to insert components with 3 legs? These questions are even easier to answer because the first great idea of Markus. You do not need to know that because the testers find the pinout automatically. But how do they do it? For that we have to dig a little into the diagram of the testers as well as the Arduino chip used in all testers. Let's start with the Arduino chip. We all know that we can switch a pin as input or as output using the command pin mode. It offers 3 possibilities: output, input, and input pull-up. Let's now take a microscope and zoom in on how the engineers at Atmel solved the problem of creating these universal pins. Here is the simplified diagram of a pin of an 80 mega chip. It has 3 resistors and 3 switches, as well as a connection to the analog to digital converter. Also, it has 2 diodes, which protect the chip if you accidentally connect the pin to a negative voltage or to more than VCC. Here is also the secret behind the 5-volt compatibility of the ESP8266, for example. On the ESP8266, VCC is only 3.3 volts, and if you connect 5 volts to a pin, this diode starts to conduct. If you would connect your power supply to the pin, a very high current would flow across this diode, and it would destroy the chip in milliseconds. But if you connect the output pin of a sensor to the pin, the current is limited by this resistor inside the sensor chip. Like that, the diode reduces the voltage to little above VCC and the ESP is not destroyed. But let's return to the component testers. Here we can forget about the 2 diodes and also the pull-up resistor because they are not needed. Let's assume we configure our pins as an output. Then the switch DD is closed and the pin is either connected via the 22 ohms resistor to VCC or via the 19 ohms resistor to ground. These values, by the way, are only approximations and can differ in reality. Now we can switch the level of the pin using the command digital right, low or high. This command moves this switch. But what happens to the level of the pin if we select pin mode input? Then DD is opened and the pin has a high impedance. It is only connected to the ADC and nearly no current can flow. Each pin can have 3 different states: ground, VCC and open. This is why such pins are also called 3-state pins. Marcus knew about that, but he knew much more. He knew that all our parts behave differently. Otherwise it would make no sense to have such a lot of different parts, right? But he had a huge problem to overcome. The only thing such a pin can measure is voltage from 0 to 5 volts. And because all MCUs use clocks, they also can measure time. And now the genius begins. He connected 2 resistors to each of the 3 test pins, and then he connected these resistors to pins of the Arduino. Besides that, he attached 1 Arduino pin directly to the test pin. Looks pretty simple. But as with all great things, it has to be simple. Everybody can build complicated things. If we simplify the drawing and arrange it a little different, we can choose of 7 possibilities for each test pin. Ground or VCC via 680 ohms resistor, open, ground or VCC via 470 kilo resistor, ground and VCC. In addition to these 7 possibilities, we can measure voltage. Now let's connect a resistor between test pin 1 and 2. If we connect pin 1 to VCC and pin 2 to ground, a current flows through the resistor. But, as said before, Arduinos only can measure voltage, no current. So Marcus selects the 680 ohms resistor for pin 1 and creates a voltage divider. Now the Arduino can measure the voltage at test pin 1 and calculate the resistor we inserted between test pin 1 and 2. Cool! Of course, we can see limitations. The accuracy of the measurement heavily depends on the accuracy of VCC, of the 680 ohms resistor and the ADC in the Arduino. VCC is usually not very precise, but as I showed in video number 10, you can adjust for that error by using a reference voltage. This is a task of the LT1004 in the original design or the TL431 in my Chinese clones. Then the suppliers should use precise 680 and 470K resistors. They do not do it. They use standard SMD parts because of the price. And the ADC of the Arduino is also only 10 bits. So do not expect high accuracy. But we will later see if this is good enough. If we talk about accuracy, we have to mention the reason for the 470K ohm resistor. It is used if we insert a high resistor of, for example, 1 mega ohm. Then the voltage at test pin 1 would be very close to VCC. Then the software changes to the 470K resistor and the voltage is much lower. This is the next trick Marcus used to get a vast range of detectable parts with acceptable accuracy. Now we are done with understanding the principle. Let's look at the next problem Marcus faced. Here you have the whole mess. Many different parts to distinguish and test. If we start with the passives, he has to detect resistors, capacitors and inductors. Then 3 types of diodes. I know diodes usually are not called passives, but the space here on the slide was handy to put them here. By the way, do you know how to separate a standard diode from a Schottky diode? Yes, the Schottky diode has a much lower forward voltage of only around 0.3 volts. The standard diode has one of approximately 0.7 volts. This is why we often use Schottky diodes in power supplies. Now you see how Marcus worked. He had to find a fingerprint for each part category. And not only that, but he had also to make sure that not 2 part types have the same fingerprint. Let's go to the active components. If we start with transistors, we have bipolar junction transistors or BJTs and field effect transistors, also called FETs. In the BJTs, we have NPN and PNP transistors. Then we have 2 categories of FETs, both available in N and P channel versions. But that's not all. We also have IGBTs, thyristors and triacs. I do not know how he thought that he could create a distinctive fingerprint for each category in this mess. But obviously he believed it, and finally he got quite good at it. On top of that, we never should forget, this device has no clue which leg is inserted in which test pin, an additional complication. And one thing you should also remember, some of these parts are very delicate and can be destroyed by overvoltage or overcurrent, especially if you do not know which pin is which and insert them the wrong way. So he has to make sure that the device never starts with a lethal voltage if it's not 100% sure. To see the tester work, let's have a look at the voltages of the 3 pins if we insert a resistor on pin 1 and 2. Pin 1 is the yellow trace, pin 2 is green and pin 3 is blue. The tester tries various things and based on each measurement it selects new tests until it is clear that a resistor is between pin 1 and 2. Then it measures its resistance and displays the result. The resistor, by the way, is a 470 ohm resistor and the bench multimeter measures 465 ohms. Not bad. If we connect the same resistor between test pin 1 and 3, the tester has to select a different test pattern, but in the end, the reading is the same. Excellent. Now let's try a capacitor. Here we have to talk a little on how we can measure capacity with this poor Arduino, which is blind on nearly all eyes and only can measure voltages and time. If we connect a resistor in series to a capacitor, it is charged over time. As you know now, the tester easily can create such a diagram, by connecting VCC via the 680 ohms resistor. And this is what we see on the oscilloscope. Pin 2 stays at ground and the capacitor is charged through pin 1. The formula is like that. If we wait a specific time, we can switch pin 1 off and measure the voltage. Now we can calculate the capacity because we know all parameters of the formula. Cool. Let's see the result. A little bit more than 2000 microfarads. But the capacitor is marked 3300 microfarads. Let's test it with a multimeter. A little bit more than 2100 microfarads. So the capacitor is oversold and the tester is okay. Good to know. Do you understand now why I love this device? As the next part, I have here a BS108 small signal MOSFET purchased on AliExpress. Let's test it. The device says it is an NPN transistor, not a FET. But how can it distinguish all these transistors? First, how can we distinguish a PNP from an NPN transistor? If you know that it is a BJT and where the pins are, you can switch the base between ground and VSS. Of course, always with the 680 ohms resistor in line. An NPN transistor turns on if you connect its base to VCC, and a PNP BJT switches on if you tie its base to ground. Also, a small current flows into the base pin or out of this pin. If the test sample is a FET, it behaves similarly, but no current should flow to or from the gate, because it is isolated. Because I bought the BS108 on AliExpress, I do not know the truth, but have some indications that the tester might be wrong in this case. The BS108 is quite a special part and might show us the borders of the component tester, so do not believe blindly to its results. If we use bread and butter MOSFETs for the tests we see, for example, it detects the right pins as well as the right category. It even shows a beautiful picture. In addition, it measures a few values and displays them too. It shows, for example, that VT of the IRLC44 is lower than the one of the IRF540. What does that mean and what can we learn here? Both are N-channel MOSFETs. We often use them to switch a load. Its source is connected to ground and its drain to the load. Gate is connected to a pin of an Arduino or an ESP. VT says at which gate source voltage, also called VGS, the FET switches on. The IRLC44 switches on at a lower voltage than the IRF540. As we see, the latter is not usable for 3.3 volt devices, because it would never switch on. If we consult the datasheets, it is confirmed. The IRLC44 starts to conduct at around 2 volts and the IRF540 at 4 volts. It looks like we were lucky with our part because it switched on at 3.6 volts. By the way, both transistors would work with 5 volt logic like an Arduino. You see, also with transistors, we not only can check to which category they belong and which pins are which, we can also check if they work correctly. I did not test thyristors or triacs because I currently do not have them in the lab. But a lot of them need higher voltages than the 5 volts of these testers. So in theory, they should be able to recognize these categories, but in reality, it often does not work. These two testers can also measure inductors, which is also handy because I have no other instrument in the lab which can do that. And the ones with a rotary encoder have a counter and a frequency generator on board, which adds even more value to the $10. Summarized, these are incredible devices and inherit a lot of engineering skills. They use modern technology at its best. Thank you, Marcus, for starting such a marvelous project. Because an Arduino only can measure time and voltage, this device has procedures to convert current, capacity or inductance into voltage and time. It has a high degree of accuracy in detecting the right pin and the correct category of an electronic part. The measuring results are okay, especially if you only want to know which value a particular part has. This is more and more important because these days it is not always easy to read the cryptic and small prints on the parts. If you are interested in how accurate the testers can be, you can look into the 130 pages of documentation. It is worth to read it also if you are interested in how you can distinguish between components. You find a link in the description. All in all, this is one of the best investments you can make for your lab. One last thing. Look at this program logic. You can imagine how much work went into this programming and how much time into finding fingerprints for every part. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the links in the description. Thank you. Bye.